Hello everyone, I will be talking about fully dynamic matching algorithms and I will be introducing order Ruzsa-Szemer edi graphs. We are particularly interested in bounding the running time of our algorithm with this type of graph. This is a joint work with my advisor, Soheil. Let's get into the problem definitions. A matching is any set of vertices joint edges. A maximum matching is a matching of the largest possible size. Our problem is to maintain an approximate maximum matching of a graph that is subject to edge insertions and deletions. For example, here, we maintain the red edges as some edges are inserted and deleted from the graph, we have to change our maintaining edges in order to keep the approximation. Now let's take a look at the previous work. There has been two lines of work. One is to maintain matching size, the other to maintain matching edges. That we'll be particularly interested in the second one. For approximation ratio, you can do half approximation in constant time per update. For 1 minus epsilon approximation, there is an algorithm by Gupta and Peng that does n time per update, and there has been some works also on maintaining matching size with n to the 1 minus epsilon time per update. We fill this gap with our algorithm that is actually the running time of our algorithm could be anywhere between a square root of m and n. This is because of the unknown parameter of the density of the order Ruzsa-Szemer edi graphs. Further, that has been improved to n to the epsilon to n. That is a work of Sepper, Sanjeev, and Peter. So let's talk about our contribution. As I mentioned, this is a randomized algorithm that maintains a 1 minus epsilon approximation. We will be introducing order Ruzsa-Szemer edi graphs in our paper. That is a generalization of the well-known Ruzsa-Szemer edi graphs. And we'll talk about the running time of our algorithm. So let's start with the definition of a Ruzsa-Szemer edi graph. This graph contains induced matching, a matching that has no other edges between its endpoint. For example, here the red matching does not have any other edges except for the matching of the edges of the matching. We define an RT-RS graph as a graph with T edge disjoint induced matching of size R. As you can see here, we have matching of size 3. We have 4 of these induced matching. That is a 3-4 RS matching. Now let's define order Ruzsa-Szemer edi graphs. The generalization is defined in a way that each matching is only induced in a matching appearing previous to it. To be more exact about it, I have to say that a graph with T edge disjoint matching M1 through MT, such that MI is an induced matching of only M1 through MI. This is an RT-ORS graph. We define ORS N of R as a maximum T for which an n-vertex RT-ORS graph exists. We similarly define RS N of R, the maximum T for which an n-vertex RT-RS graph exists. This is an example of ORS graph. M1 is not induced in M2, but M2 is induced in M1. This means that actually each RS graph is also an ORS graph, but the other way around is not actually true. So let's take a look at our key result here. That is, there is a randomized fully dynamic algorithm that maintains a 1 minus epsilon approximation maximum matching, and the running time is almost square root of n times the density of ORS. So now let's see how we can what are the upper bounds and lower lower bounds for the density of this type of graph. For RS graph, what we know is that we can lower bound it by, let's say, n to the little o1, and upper bound it by n to the 1 minus little o1. And since each RS graph is also an RS graph, the lower bound also applies for ORS graph. This is a lower bound of n to the 1 little o1 for ORS graphs. And in our paper, we actually proved that we can almost get the same upper bound for ORS graphs as well. And this does not apply simply because we don't know actually because it's not actually true that each ORS graph is an ORS graph. So we prove an upper bound of n to the 1 minus little o1 for ORS graphs as well. So now let me talk about an example here that gives us some intuition why this structure appears in the problem of dynamic matching. Let's assume that we are given an ORS gadget graph G in our dynamic graph, and the adversary will do the following. Let's say it would pick one matching from MT to M1, and it would connect its complement nodes to the outside. So in order to find this matching, we have to actually to find a good approximation for this matching, we have to identify this the matching of these ORS gadget here. And then the adversary goes on and removes all the edges and does the same thing for another matching in the ORS gadget. What we need to do is at each time go through all the edges of the ORS gadget, and we have to spend NT time because we have T matching, we have almost NT edges. We have to spend NT time for each matching, and that would be in total NT squared. And if we amortize it per updates, we get NT squared over NT, that is T, the running time would be T, that is actually the density of ORS graphs, the size of the ORS graph. So this is why this actually appears here. And so now let's take a look at some of the tools that we have in order to solve the dynamic matching for the approximation ratio of 1 minus epsilon. The first tool is that we can actually assume that the maximum matching size is of order n, and using the assumption, we can find a matching once and do nothing for the next epsilon n updates. The second one is that for solving a 1 minus epsilon approximation, this actually reduces to finding a constant approximation on some queried subgraph of G, such that each subgraph contains a large matching. So we are given some subgraphs that we have to find a constant approximation for each of those, and these subgraphs are chosen by another algorithm. So this is all we have to do. The problem reduces to starting with a graph, receiving epsilon edges, and then epsilon n updates that could be inserting and deleting, and then we'll receive some query subgraph U, and the task would be to return a constant approximation matching in each of these queried subgraphs. The main lemma that we use to find this matching is the following, that actually uses random sampling. So we are given the subgraph U. We prove we find actually certificate matching in this subgraph that is actually large enough matching, and this algorithm will run in n squared over d. What d is the average degree of a matching that I'm going to define by counting all the edges um, that have both endpoints in the vertex set of this matching and divided by the size of the matching. This is the definition of the average degree of the matching that I'll be using in this talk. The way that this algorithm works is the following. We would fix an unmatched vertex B and then sample some vertices. And if one of these vertices has an edge to V, we would add this to the matching if it's not already added. And if the degree of V, let's say degree of V is dV, then it takes almost n over dV to find an edge. So overall, we're going to spend n squared over d to find this matching. The point that I want to mention here is that if MC is an induced matching, it would take us n squared sample, almost n squared sample to find this matching. This means that we aim to actually charge this examples that have contain induced matching to the ORS graph. This will be our hope to get a running time based on the density of this type of graph. So let's take a look at what our algorithm does. We're given a graph G. We'll keep track of the inserted edges and the certificate matchings. And we have also another graph that we just delete all these edges from, all the inserted and the certificate matching edges from G, and we also keep track of this graph. Now, let's say we're given some subset U, and we want to find a matching for subset U. So we go through G add and the certificate matching, and if we find a matching, we would add it. But if not, we have to pay this cost that is actually a lot of cost, that is n squared over d1. Let's say this is the average matching of this matching here. We pay the blue matching, we pay this cost and add it to the certificate matching. We don't want to go again and look for some matching that we already found. This is the reason why we keep track of the certificate matching in order to lower our cost of doing the same thing again and again. Then our graph goes through, let's say, epsilon and insertions and deletions, and we are given some other subset. Let's say this subset U, that is the red vertices. Now again, we have to go through all the edges of the inserted edges and the certificate matching. And if we could find a matching there, we would add it. So it would take G add the number of edges in G add and edge cert to be able to do this. If we were not able to do it, again, we're going to give a cost of n squared over d2 this time to find a matching in the new subset view. And we will just continue to do this. And this is actually how our algorithm looks like. Something that we actually want to do is to make sure that these huge costs that we are paying, we want to charge those to the ORS graph. But we might have this something like this, that we find a matching. This is not actually an induced matching in the matchings that we found already, yet it is just a sparse that we just have to pay a lot of time to find this matching. We solve this problem using this lemma here. That is says, if we are given a graph G, that is a union of some matchings, and we look at its the degree of this each matching DI in the matchings that appeared before it. This is the average degree in the edge set of the matchings that were appearing earlier on from this matching. Then we can actually bound the sum of 1 over di by log n ORS of n. We will be applying this lemma simply using the certificate matchings. We have to be careful about the order here, and also the fact that this graph G minus G add minus a certificate is always a decremental graph will help us to apply this lemma. Now using this lemma, we can bound the sum of n squared, the sum of 1 over di times n squared by n squared times ORS of n. Finally, we get to the running time analysis. That is, let's say we give an upper bound for the size of G add and the certificate graphs. We are going to pay these costs of G add a certificate at each epsilon n update times. And we actually can reset these two graphs if they get super large. So we can also amortize the running time that was n squared times ORS of n over the size of these two graphs. And by picking this threshold for the size of these graphs, we actually get to the square root of n ORS running time. And I want to finish my presentation with an interesting open problem, that is whether it is true that we can bound the density of ORS graphs with RS graph. As we know, the other way around is simple, but we don't know anything of this sort. So that would be interesting. Yeah, thanks for listening. This was my talk.